Hi, my name is Trenton Kaysen, and I'm going to be talking about how to use R and RStudio using Tidyverse to analyze, preprocess, and make conclusions from data. And this is going to be from an engineer's perspective, so it's going to be highly practical and not very deep into the weeds. There's a lot of people who know a lot more about these topics than I do, and certainly some of them will be in the comments, and I'm sure they'll have great insights into things that we could do better. But as far as getting us started and getting people comfortable in R, I think what we're going to do is going to be a great start. So right now we're looking at RStudio, which is an integrated development environment. This is where we'll primarily be writing our code. If you're familiar with other scripting languages, this may seem familiar. Whoops. This may seem familiar, so we can just type in a script here, and I just ran this by hitting Control Enter. And before you saw me make this error, I just hit Enter instead of Control Enter. And when I did that, it actually ran it in the console. So your first Hello World script in R could be as simple as just typing Hello World, and you're done. There's nothing particularly special about saving or compiling. Most of these things happen inline, which is both a pro and a con. The pro is that you can kind of write code really quickly. R is made to be highly compact, highly efficient to write, but that does mean that it's going to be a little bit slower to run in certain circumstances. But definitely not too bad of a weakness because most of the work is actually happening on the data cleanup stage, so where we're actually going to be thinking about the data. Anyway, but how do you even get this? So RStudio is an integrated development environment, and it's one of a couple of options, but you could just type in RStudio into Google or Bing or whatever, and you can go onto the RStudio page. We're actually going to be using another thing that's made by this company. It's called a Tidyverse. You can go up to this download section here, and you can just get the desktop one if you're just using it for yourself, or if you happen to like it and you want to use it in a work environment, you can use RStudio Desktop Pro. It's a little bit expensive, but you get a couple of other advantages. You can connect to it remotely, which is very convenient. So in this case, you can just hit this download button, and it'll pull up. It'll try to interpret what your operating system is. In this case, I'm on Windows. You can just download that. But also, if you're on Mac or Ubuntu, Fedora, your other Linux distros, they're going to be in there too. This is your integrated development environment. This is actually going to be what you're going to be writing the code in. However, this would be nothing without your backend, which is actually the language R itself. That's actually what we see here, and we have an option to run Python if we wanted to. And that you'll get from CRAN. Usually, for me, the easiest way to find this is to type CRAN R. And CRAN is just the R archive network. It's not a very pretty website, but that doesn't necessarily matter. But if you go on the website, you can pre-download whatever version of R you need. In this case, I'm on Windows. And you might see this screen, and this might be a little bit scary. But the base R, this is actually going to be the thing that runs the code. This is going to be contributed R packages. You probably won't need this unless you're planning on writing your own packages and use the old contributions. And then R tools, this is to use for building your own packages, or if you potentially want to download a pre-production version of a package, this will be able to compile the binaries. For our use case, all you just have to do is click base, and then we're going to download that most recent version. There may be a more recent version by the time this video comes out. They put up new versions quite often, and that's totally okay. It looks like this last one was exactly a month ago. So mostly new versions are going to be quick fixes for things, or potentially add in a couple of extra features. And if you're ever interested in what those features are, you can always hit this new features in this version, and you'll get a lot of nice info. One big advantage of being open source is that they try to be very open with the community and tell everybody what's happening, so everybody can be on the same page, especially if this is going to be used in a business context to potentially make somebody some money. All right, we've got R, we've got RStudio. You just install them. You can use your standard settings if you want. Now you're in here. Potentially one thing you might want to do, at least for me, if you're familiar with other integrated development environments, or you're just working in a dark room, you might want to go into the appearance settings here and pick something dark, just like dark mode in your web browser. I don't really like this black bar here, but you can just kind of check through here and see which ones you like. But there's potentially some viewers who could be red green colorblind, so this might be a little bit hard to read. So I'm going to see if I can find another one that I like here really quickly. I'm going to pick something high contrast. Yeah, this seems good enough. So I'll just hit apply, and bam, we're in. Okay, so now we have R, we've got RStudio. The next step is to actually get your data source. So you may already have a set of data that you're interested in using, and that's perfectly fine. If you're still kind of getting used to R, there's actually uh, their own data sets in here. So if you want to just kind of use something that comes straight with R, you can check out these. I don't know what all of these are, but some of the ones you'll commonly see, you'll see things like empty cars, or you may also see iris a lot. And these are just really simple starter data sets. But I believe that this is a little bit confusing for people who may be new to R in general, because this isn't really how you would download exogenous or outside data. So you can run this line and it'll create this iris thing. It says promise right now because and things that are loaded lazily is what they call it. Just it's not actually going to try to go get this until we tell it to. So if we wanted to check out what that data set looks like, we can type head, which is going to just take the top 6 rows by default of our data set. And now, as I typed it in, it interpreted that, okay, we're actually going to need this data set. So I'm going to go ahead and preload it. And you saw that the promise went to 150 observations of 5 variables. That means we have 5 columns and 150 rows. And if we check this out, this is just kind of a quick set of what this data looks like. And just another quick look at that data. You can type summary and it'll spit out your quantiles, which is kind of convenient for getting a sense of it. And we'll go into a little bit more detail in a second. But first, I'm going to show you also how to ingest data from another data source. Give me just one second. All right, so if you need some data and you don't have something already in mind, that's perfectly okay. We can go to Kaggle. Kaggle is a data science community online. They hold these cool competitions that certainly have pretty high payouts if you are the winning team. Some of these are going to require tools that we don't yet have in our tool belt, but certainly fun to try if you can. There's also going to be nice knowledge challenges in here too, so it can be a lot of fun. In this case, we're actually going to go to the Datasets tab, and you'll see there's lots of stuff in here. We can just look in the education or something like this, and we'll see all kinds of neat data sets in here. And I think actually for this one, I'd like to use this red wine quality, just something that's pretty simple. There's not too much data in here, and we'll be able to check it out relatively quickly. Just in case you've never used Kaggle before, you can download it here with this download button. And you can kind of get a quick summary of your data. Go to this column here. This is a histogram, and I'm not exactly sure what these mean, but we'll be able to analyze it. Anyway, it looks like we have about 1,600 records in here, which is great. That's quite a bit of data. So having a little bit of domain knowledge is always a little bit more helpful whenever you're trying to make predictions. But for now, I'm just trying to get comfortable in R and processing data. Certainly not a requirement. So this is our data set. I've actually already downloaded it, and it's in my R YouTube folder here. So one hot tip, if you're on Windows, if you shift right click on a file, you actually open up a special copy window, and there's a I guess you have to do it over the text on the name. I didn't know that, but you actually see this copy as path option here, and the hotkey for this is A. So you can hit A, and you'll have a copy to your clipboard, and then you can just paste it, Control V, into your R script. Now there's one thing to note in ingesting data into your R script is that if you're on a Windows machine, and a Windows machine only, Windows uses backslashes as the navigation through your folders in your folders. But R is actually interpreting these backslashes as an escape character, basically something that says, hey, I know that this is in a string, but I actually need the system itself to run this. So we have two options. We could either go in here and replace all of these backslashes with forward slashes, and it will read it just fine. Or we could replace all those backslashes with double backslashes. I'm going to do the forward slashes just because it's a little bit more compact, but certainly do whatever you're comfortable with. So here's our string. This is actually just the text of the file path, but if we just run this, R is just going to interpret that as, okay, this is a string. I don't necessarily know what you want me to do with it, so I'll print it to the screen, which is fantastic that it did something with it, but not actually what we wanted this time. So what we're going to do is we're going to ingest this data. And I said a little bit earlier that we're going to be using a package called Tidyverse. And this is actually a whole collection of packages that have really convenient functions in here. And you can actually do, you can download a whole bunch of them all at once. But you, like me, I'm on a new version of R right now. If I try to run this, it's going to say, hey, you have no package called Tidyverse. So what do? We have two options. Since we're in RStudio, and I'll show you how to do it if you're just in base R, but since we're in RStudio, you could go into Packages, click this Install button here. You can type Tidyverse, and you could click it and hit Install. And this install dependencies will also go get anything else that Tidyverse is referencing in its own packages that might be useful. That's certainly something you can do. Also, if you're just going to be in your base R, you can do install.packages, and you'll actually see that whenever we were going to do that with this install button here, it would do this exact same thing. So just for posterity, we're going to do this install.packages tidyverse, and you may get this message here that says, actually we have two messages here. The first one here is that your library is unspecified. This isn't necessarily important. This just means that I haven't actually called out exactly where I want this library to be. Now this message here says, do you want to install from sources the package which needs compilation? This is back to that RTools question earlier, whether or not you wanted to potentially install like a pre-production version of a package. In this case, you don't actually have to hit yes on this one. If you did, it would try to do it and then say, hey, you don't actually have RTools. I don't know how to actually do this. So no, we're not missing out on anything by hitting no on this question. So everything is going to download here. And there's several packages inside of this that are getting referenced, but this may take just a second. But Tidyverse has a lot of really convenient functions in it that allows us to ingest and manipulate data, and that's actually what we're going to be primarily using. The reason why I'm using Tidyverse over base R is I believe, honestly, that Tidyverse is the way of the future with coding in R, and it's something that really differentiates data processing in R over something like Python. We can actually pipe together multiple functions. So we're going to be able to do that right now. So now, just like before, we're going to try this library. This just means, hey, please load up all the functions and all the packages necessary in this thing called Tidyverse. I hit Control Enter on that. It's going to take just a second, and it told us, hey, okay, I attached all these packages. Now I have access to several extra functions. All right, and so what's the first step? So the first step is going to be to ingest our CSV file. So there are two ways to do this. In the future, I believe we'll use Room, which actually looks to be available now. So we could certainly do that, but I'm going to use Reader, which is just a little bit more, I think, user-friendly at this point. So Reader is just like a generic way to ingest files. So if you type reader here, and I was typing : to access actually the internal functions that are in this package, just in case they weren't actually available. Actually, and you may not need to know this, but if you hit : this is actually going to be the function that it's calling on the inside. So you'll almost certainly never need these, but sometimes it's nice to know what's in here. But for now, I'm just going to type reader, and I'm going to actually look for something that's called read CSV. And this is just going to interpret our CSV. So now we have a couple of options here, file, column names, etc. But say you accidentally hit escape and you can't see that, you can always get back to that by hitting Control Space, and it's going to be in just a different format. So this is going to bring up your IntelliSense. So the first argument in here is file, and you can hit, if you select through here, I'm just using the number keys. If you select through here, you can hit Tab, and we already have our file here, so I'm just going to cut. Oops, I'm just going to cut this over, so Control X, and I can put that right in there. And then call names, I actually don't remember what they are. Let's just see what happens. And if we don't assign this to anything at the beginning, it's just going to print it out to the screen, which is perfectly fine. I don't mind that. So now we have this printed it out to the screen and told us a little bit about, hey, when I interpreted your data, here's what I saw. Here's how I specified your data. There's a very high likelihood that it may have interpreted something incorrectly. It's just totally okay. Actually, it looks like in this case, though, because our data is relatively simple, it's all numeric. We actually probably got away with it. But say you had a character vector or something in here, we would maybe need to do something a little bit more specific. But for now, I think we got away with it, so that's okay. And then, but how do we actually work with this data? Let's go ahead and save it to a data frame. So a data frame is actually just a in-memory representation of our tabular data here. So I'm going to store this to a data frame. So you could certainly use just something simple like data, but I find that a best coding practice, especially if you're ingesting lots and lots of different data sources, it's better to use something that's relative to your data itself. So I'm actually going to call this wine quality data. And just one other note here, if you're coming from something like Java or Python, you might see underscores or periods in place of I don't know, a camel case or something like that. In R, there's no difference. It doesn't read these dots as an activation of a method or anything. So I may use these interchangeably, and certainly some people would be offended, but just for me, it's a little bit easier to use a underscore. So I'm going to go ahead and run this code. And now we have wine quality. Here's the same information we saw earlier, almost 1,600 records, 12 variables. And now, okay, we got our data, we got it stored in a data frame, and we can tell it's a data frame by typing wine quality data. And then this will just tell us like, hey, this is a data frame table, and these are just all the different features of it. You may never need to use this class argument unless you're dealing with like kind of a weird data type. But this is certainly one option. Also, I noticed that I did something up here that might have seemed a little bit strange. In many languages, you'll see this kind of equal sign here whenever you're setting a variable to some piece of information. And you can actually do that, and I'll prove that here in a second. You can actually do that in R. That's totally okay. But traditionally, in R, it's actually written as a left pointing arrow. And the way you would interpret this is gets. And these do exactly the same thing. Nothing changes. But I tend to use this just for extra clarity. So, and there is a hotkey for this in the tools. You can actually go in and show your keyboard shortcuts, and you can modify them. And there's all kinds of them in there, and we'll end up using some of them. But for me, I have this set to control and less than. Oh, excuse me. Control. Yeah, okay. Control shift less than. And just as a little bit of a time saver. So now we've got our data here. So what do we do? So there's another very convenient package called Skimmer, which doesn't get pre-installed with Tidyverse. So I'm just going to install this really quickly. And take it just a second. It's installing a couple of different packages. And now inside of Skimmer, there's actually just a function called skim. And we can just take our data, then we can just check it out. So what this does is it kind of creates sort of those same histograms. These are called spark charts that we saw in Kaggle, but it shows it in our data itself. And if we were to make any sort of manipulations of this data or something, it would represent that as the data is actually in our data set. So I tend to use this whenever I'm looking at brand new data sets or something, because it's a really nice summary. And the alternative that you may have seen me do earlier would have been something like summary, which does many of the same things. You can see this P0. This is the minimum. These are all the quantiles again. But we get a couple of extra pieces of information about the number of missing data points, and then that percentage complete. And then we get these nice histograms, which can be convenient. And also, if we'd had non-numeric data types, there would actually be extra pieces of information spit out. Okay, so enough waffling. Let's process this data. So, all right, the very first thing that we could do to this data set is just try to do a quick linear regression. So I'm going to try to predict this quality just the way it is right now. Although in a minute we'll talk about potentially why this may not be ideal. And we're just going to say, hey, quality, let's see if we can use all of these other variables to try to predict quality. And I haven't done this before, so I'm not exactly sure what the output's going to look like here. But just like I had done earlier, I'm going to save my linear model with just this wine quality prefix here. And the function to do a linear model in R, it's actually just ln. The formula syntax in R is just a little bit confusing, or at least it was to me when I first got started. But you'll say, okay, on the left side, this is going to be the variable that I'm going to try to predict. So I'm going to be trying to predict quality, and it's going to be predicted with this little tilde here is going to tell us predicted with. And I think in a lot of the examples you'll see online, you'll see just this period here, which to me seems extremely arcane. But really all that period means is it's just taking all of these different fields, these fixed acidity, volatile acidity, etc., and just says this just means everything. So if we wanted to, we could just take a look at quality as just a function of pH, and then we need to tell what our data is. And if we want to be super careful, we could say formula equals that. Our data equals this, and our data here is just this wine quality data. So nothing super fancy here. It ran okay. You can always tell too whenever you see something come out in the environment here. And so now we can take this, and we have two options. We can just print it out in the console, and we'll get a little bit of information about it. We actually see here's our coefficients. Or if you want just a little bit more information about our object, we can actually type summary here, and here's those are those coefficients, but we also get our p-values here, which are kind of convenient too. So in this case, if you remember from your stats class, or maybe you haven't had one yet, if your p-value is low, you should reject the null hypothesis that the variable does not have an effect on the outcome. So in this case, using the standard p, alpha of 95, your p-value of 0.05, you would probably say, okay, I think pH does have an impact on the quality, and actually the impact is negative. So as the pH goes up, the quality seems to go down. But note that pH actually, just more information about this is why it's useful to have a little bit of domain knowledge. pH tends to be centered around 7, right? 7 is a standard pH, but in this case, actually in our data set, it's not. These are actually pretty far off from 7. So I was going to try to say basic or acidic, but to be completely honest, I don't remember, so I don't want to say it wrong. But we could definitely look it up. All right, so that's just to do it with pH. Let's do it with everything. So we'll do the dot instead, or if you wanted to exclude something, for example, we could just type minus pH, and this would run it with everything except pH, and we'll see here in the outputs, we don't see pH. And if I do this again, oops. We can see pH in the output here. So this would just be a really simple regression, and this is how we got our linear regression. So it looks like we have a couple of these variables here that seem to be kind of impactful. The number of chlorides seems to have an impact, and actually having less chlorides seems to have a positive impact on the quality, or in other words, more chlorides has a negative impact on the quality. I kind of said that in reverse, but basically this estimate, all these values are going to be multiplied by the variable, and you're going to sum up the product of the estimate, this is your coefficient, times whatever the term is, and that will give you your output. So just to make sure that's super clear, if our do a quick estimate here. So if you do this colon here, you get a sequence of numbers. So let's just say this is our chlorides value here. So we'll just take this number straight out of here. This isn't necessarily the best way to do it, but just for clarification, if we were going to take each of these values, so from chlorides going from 1 to 10, just like this, and we multiply it by our coefficient here, assuming this is the only coefficient. That means that the result is going to be what we predicted, which is this quality here. And so we see that as the chlorides go up, the quality actually goes down. Now, as we saw in our skim up above, the chlorides actually don't range that high. They're between 0.12 and 0.6. So if we wanted to just be super careful, we can do a sequence. This is basically just like our colon there, but it's just another way to write it. We can do 0 to 1. We can do that by, I don't know, 0.05 or something. And then now we can see as the chlorides go up, this is going to have a negative impact. So if you had up to, whatever 1 is in our units up here in our chloride, that would actually deteriorate the quality of your wine by, almost 2 points. So potentially very impactful. Okay, so this is base R of how to do a prediction. And I don't think that there's too much of a better way to do at least a linear regression that's easy to interpret. But there is an extra function called tidy, which comes out of the Tidyverse, and it's in this package called Broom. And this is just kind of a nice, convenient way to represent those coefficients. So this actually spits it out in a data type called a tibble, which is the same information we saw here, but just a little bit easier to interpret, at least in my opinion. All right, so you may be a little bit disappointed that I didn't get into a little bit more of the data processing side, and I perfectly understand that. So I took a moment to look at this, and I looked up the pH scale, and less than 7 is acidic. So one thing to note about the pH scale, though, is it's logarithmic, which actually we can show a logarithm here in R relatively easily. There's a function in R called plot, and all you have to do is provide x and y, and it's just going to do a scatter plot of your data. So if we just take a moment to plot some values, let's say, let's plot from 0 to 100. So we'll have 100 data points. Or 1 to 100, we'll have 100 data points. And then let's plot on a y-axis. We'll plot the log of that. So just in case you're unfamiliar with logs, this will give you kind of a sense of like what's happening. So if we were just plotting 1 to 1, right, so you just see a straight line. So as the x goes up by 1, the y would go up by 1. But with a log, if the x goes up by 1, not necessarily that the y would go up by 1, it's actually a variable. And so that means while we're looking at the pH here, and your p-value is low, in my opinion, this would probably be useful enough to use. Perhaps there's an opportunity to take the log, or excuse me, the exponent. We're going to invert the log of this data. So say we have the log here. If we take the exponent of it, we'll get our straight line again. So we see that, and bam, we're back to our straight line. So the same data. So one thing that we could do to pre-process our data is to take the exponent of that value. So one thing I like to do whenever I'm pre-processing my data is I like to kind of have two data sources, because oftentimes I get a little bit excited and I may potentially remove an important feature of my data, and I don't want to remove it and not have a backup and have to, go through a potentially kind of expensive process to get it all back, especially if you're on like a database or something and you have to pull your data and you're pulling lots of data. It's kind of convenient to just, leave one version stored in memory, and then I'll create another one, right? And I will usually prepend these with the word clean. Certainly not the only way to do it. You could call it whatever you want. But in this, I'll just take my wine quality data. And then here I'm going to get into kind of the first piece of the puzzle for Tidyverse. So I'm going to use what we see here as a pipe. So this pipe, really what's going on behind the scenes is not super important. All I think you really need to know about it is that you can kind of just read it as a series of steps. So we're going to, and I'll describe it here in a second, but we're going to say, okay, take the wine quality data and we're going to mutate it. So we're going to take it and we're going to change it in some way. And then we're going to, after we're done with that, we'll print it. We'll just do kind of a nice, simple series of operations here. So wine quality data, that gets to mutated, and then that's going to eventually be printed. So I'm going to go ahead and fill out this one argument here with what we were talking about here with the exponent or log of our pH, and we'll go from there. So the first thing here, so we could overwrite the initial data pH, and we could just take the exponent of it, and that's totally okay. And if we do that, we'll see now the pH value, or it's actually being hidden. So what I'll do here when I'm printing it, I will do as.data frame, which is just going to print it in a different format, or actually, I guess not. So, and I will go back and I'll try this a different way. We'll do as data frame here instead. There we go. So I was thinking I could sneak it into this, but I guess not. So one weakness of printing it all to the data frame, and one reason why it's kind of nice to have this tibble, is that it prints it prettily, but it doesn't always print all the variables that I'm interested in. And you can certainly, if you're just interested in looking certain values or something, you could type select, which is just going to grab certain columns. And in this case, if I only wanted to look at pH, I could just print that one out. But what I've done here, this print really just returns the data. So I had my clean wine quality data set. I actually only have the one column now, so I don't necessarily want to do that. So in this case, that's probably not the best way to do it. So another way I could do it is I could just take my data here, and I'm probably I got a little bit of a crutch here, but I will often throw these quick looks into the console here. So so this is just going to take the clean wine quality data. I'm just going to convert it to a data frame instead of this tibble data type. And then we're going to take the head of that. And actually, maybe one quick way to represent what's happening in the pipe, that same operation that we were doing a second ago can also be written as this, data frame head. So we get the exact same output here. We're just taking the clean quality data, we're going to pass it to this function as data frame, and then we're going to pass that to the other function called head, which is going to take the next 6 characters, or excuse me, the next 6 rows of this. And then there's actually kind of an implicit step here, which is print, which is what's actually happening here. And if we could make it explicit, we could actually call it out, and we'll actually get that thing here too. And here now we see pH is on the linear scale. So that's going to be your percent of, I think it's hydroxide, hydrogen. Let's see here. Whatever this H plus is, I can't remember. It's been a little while since I've been in my chemistry class, but that's going to be now on that linear scale. So potentially we could see better results. So we could do another linear model. So I'll just kind of go up and grab that. But I'm gonna call it linear pH. And I just kind of formatted this in a nice way. So I just went up and hit enter to make it nice. So if it gets kind of wonky or something, you can do that. And then now, instead of using the wine quality data, I actually want to use this clean wine quality data. And so now our linear regression is done. And just like before, I'll do broom, tidy, and check it out. So now pH has a slightly lower p-value, which doesn't necessarily matter, but we do have a different coefficient. So we can compare that to just the original model here and kind of take another look here. So this is based on the linear pH. This is based on the standard logarithmic scale pH. So we can see the coefficient is different. So that's just one thing to note. And we may see like a slight variation in some of these other variables. Some of this could just be due to it could be due to our change, but it also could be a little bit due to randomness too. So certainly nothing to be concerned about. All right, so another thing you may be asking is like, okay, great, we made a linear model. Now what the heck do I do with it? Well, you can actually just call predict on it. And in this case, I'm going to predict on our linear, but it doesn't really matter. And then the next option in here is new data. So what data do we want to predict on? So you can pass in brand new data. It's just got to look like your original data. So something like this. It's got to have all these columns in there, or at least all the columns that you predicted on. So if we had excluded some variable, then it wouldn't necessarily need to have that in there. But this is going to print out a vector, so a group basically like an array of data points. So, and this is just going to be the prediction of quality, which is what we told it we're actually predicting. So, if you just ran this, you just get this giant record of stuff here, and it prints it out to the screen, which is not super helpful. So maybe we want to store that. So I will tend to call this something like wine quality, maybe call it linear pH, and then I'll just throw pred at the end just so I know it's a prediction. So, and the one thing we'll know about this is when when we look at it in the environment here. This is our wine quality pred. I gave it such a long name; it's hard to see. But this has the same number of rows as the new data, the data that we passed into here. So same number. But if we had just as a test, if we had only passed in, say the first 100 rows of this. So one way to get to a subset of your data is to use this bracket operator, and the first option is rows, and the next option is columns. So in this case, I'm just taking this 1 to 100, and I was just providing this list to the data frame, and then it's going to know, okay, well, I only need to print these first 100 rows. See, so I've got 10 here, and I can print 90 more. Or in other words, here's 100 by 12. So so now if I get my prediction, now it's only to 100 rows. So if your new data looks different, it'll be okay. You'll just have that number of rows. So now I've got my prediction here, and we can take a look at it. So we can take our wine quality data and we can actually just straight up compare the prediction with the actual. So one way we can do that is with plot, just like we did earlier. And we're just going to take our actual, so in this case it's called quality, and our new, this $sign just allows us to access the actual column names. So for example, I didn't remember what the variable is called, even though it's right in front of me. But we can just go through here, go through all the different options for this thing. This is also, if you knew the position of it or something, you could say, I want to get it with this this bracket operator that we did earlier, and then I would just need to know which one it is. It's the last one. I think there's 12 columns, so if I do this 12, I'll just test this really quickly in the console. We do get quality, so that's one other option. I find that for me, at least, when I'm looking back at my old code, it's a little bit easier for me to refer to things based on their name, but certainly there's a time and place for everything. So anyway, we're going to plot our predictions versus our actuals. So in this case, we just have this name number here, so we can just use this, and there's nothing else in this thing. It's just this list of numbers. So we don't need to use the $sign. In fact, if we did the $sign, nothing pops up. There's nothing in there. It's not something we need to do. So now we can plot this, and we can see our predictions actually look decent. I'm actually pretty happy with this. So so this is our prediction here, and we can see there's a decent trend of so this is the actual, right? So 3 on average, this seems to go below 4 to 5.5, and then from 4 4.5 to 6.5, 4.5 to 7. So anyway, it seems to go up, but it also doesn't seem to be a particularly good representation of the true data. And one way you can assess the quality of that is through a function called R squared, or we could calculate the R squared, but I believe there's a function here, so let's see here. I think it comes out of stats. Nope, it doesn't come out of stats. Let's see here. So in the case where you may not remember, you can always just type help, and then we can just see here. In that case, it's like, hey, I don't really know what you mean by that. Let's try R2. And then what this does here is it just produces the search results here, and we can always just go into this help. And so before we were looking at plots, we could always just go into this help menu here, and it searched it. Let's see here. So let's see if I can find R squared. So I don't see it in here, and to be completely honest, I don't remember which package it comes out of, but I do know that this is also in another package that we'll end up using at some point. It comes out of this package called Caret. This is classification and regression training. So I'm going to just install this package really quickly, and then we will go from there. So give me just 1 second. All right, so now our package is downloaded, and inside the caret package there is a very convenient R squared. The reason why I'm using this one and not like potentially calculating on my own is that R squared on its own is kind of a confusing thing to calculate, but not impossible. Certainly something you could do. It was created before computers were around, so definitely something you could do by hand, but I just don't necessarily want to do it. So it has two arguments that we're going to need. So first one is pred, so that's going to be our prediction. What do we actually get out of our model? And then the second one is obs. That's going to be your observation. That's like truly what was the result, so that we can compare. So just like we had here, just like in our plot, so this, we can get a value. So how good is our model? And the answer is not super great. So this value scales between 0 and 1. And closer to 1, the better. And we're at 0.36, so definitely not a great model to start with. And another way to assess, there's actually 3 that are pretty common. And inside of caret, they're all in here, which is very convenient. So the first way is MAE, that's a mean absolute error. So this is on average, what's the error rate? What's the difference between your predicted value and your actual value? So in this case, about 0.5. So I think the way to interpret this would be to say, hey, on average, I'm within 0.5 of the true answer. So not, maybe that's not too bad. Depends on your domain, right? So if you're trying to predict something in dollars, perhaps, if you're, within 50 cents, perhaps this is okay. But if you're trying to predict something that's, on a much smaller scale and 0.5 is a big deal, then this mean error rate could be a different thing. So that's one advantage of R squared over mean absolute error, or indeed root mean squared error, which is this RMSE, is that R squared is always scaled between 0 and 1. But there is a weakness with R squared in that if you have very variable data, if you have lots of noise, it'll kind of influence your R squared to be potentially lower than maybe it truly needs to be. So root mean squared error is, again, in the same units as mean absolute error, which is the same units as the actual variable we're trying to predict, but it's going to be a little bit more influenced by your highly outlier variables, so things that are very far off from the true value. So, and all this is this is just the these are pretty easy to calculate. This is just the average of the absolute value of the difference between your quality and your prediction. So just to show maybe also how to do a little bit of math inside of R really quickly. If we, and I'll show a kind of a neat feature of R. If we just take the true value and we subtract the prediction, if you're coming from something like Python or C++ or something, this may kind of blow your mind, but R will internally say, okay, well, I know this is a list, and this is a list of data. I mean, not technically a list; these are actually vectors, but and these are the same length, and we're having to do subtraction on it. So I'm going to do it to every item in this thing, and I'm going to subtract out every item in this thing, just in line. So we actually get our predictions here, so which can be kind of convenient. So, and if we take the absolute value of that, and then we take the mean, we get 0.5, which, just in case you don't remember, this is exactly the same value as the mean absolute error. And if you're looking at the root mean squared error, it's going to be the same idea. So I may not get this on the first try, so it can be just a little bit of a leeway here, but root mean squared error, so this is going to be, so what we've got here, this is just the error term, so we're going to take this, we're going to square it, okay, and then we're going to take the, so this square here, this is also going to take, it'll take the difference between the first value here, and square that, and then it'll go to the next value and the next value and the next value. So we'll still get a list. In fact, we can check the length of this really quickly. We'll still get a list of 1599 here. So, and this will just be each of these values squared. Okay, so root mean squared error. So we've got the error, we've squared it. Now let's take the average of it. So we're going to take the mean, and then we're going to take the square root of that. So squirt. and then that's 0.645, which if I did this right, and I hope I did, it matches. So just to hopefully demystify two of those variables here. So that's how we can kind of assess our quality. All right, so at this point, you might be thinking, well, Trent, this is really cool or whatever, but you haven't really shown me how to use Tidyverse, and you made a really bad model. So at least give me something out of this. And for that, I would say I totally agree. So let's start with this. So I'm just going to create like a little break here. The pound sign or the hashtag, whichever generation you're from, is the comment. So I get this is a comment, and if you try to run this, and I spell comment wrong, I'm aware, but I'm an engineer, give me a break. It actually doesn't run anything, but if we below that I typed, this is not a comment, you actually see it pop out, but it doesn't get evaluated. So anyway, I'm just going to kind of put a little break in here just so this is easier to read. And then I'm going to show you actually what I think is honestly one of our really powerful techniques that we can do with the Tidyverse. So I'm going to go ahead and take kind of the starting point we had here, and I'm just going to call this, we're going to create a new variable, and I'm going to create a couple new lines here just to give myself some space. And we're going to create a new variable, and this is going to be kind of all the work we did up here, minus the plot, I guess. All the work we did up here, but in one object, and I'll show you one other thing that would be convenient, depending on your data source. But let's call this let's go TC train, and this is gonna be TC wine quality bread data frame. I don't know, not a great name. Also, I didn't spell anything correctly here. But quality T. All right, there we go. All right, through hard work and effort, we finally got there. So, all right, so this is going to be this wine quality data, and it's up to you whether you have this on this line or this line. To me, this is a little bit easier to read, but certainly up to your preference. Okay, so say you've got this data and you really want to do all this stuff in line, right? Like Trent, you told me about the pipe, it seems pretty cool or whatever, but like, how is this useful? All right, here's how it's useful. This function nest allows us to create a list of our data, and then we can perform operations on that list of data. Okay, so in here, and I'm really struggling with spelling today. In here, we can actually create this nest of our data. So, and we're just going to straight up call it data, all lowercase. And if we do this, we'll see now where our data had been this kind of pretty, tabular data set, right? So this, has, almost 1,600 rows, 12 columns. Now we have one row, one column, and that one row and one column is just this variable called data. This is a column called data. And actually, if we store this, we'll actually see there's only one thing in here, $. We just see data, and you actually see this kind of weird symbol here. This tells us that's it's a more complex object. So actually, just for recursion purposes, just so you know, you can hit the $sign again inside of this thing, and you'd be able to get to its internal objects. Or actually, excuse me, now you'd be able to get to its internal objects. So what have I done here? So data, if you just do this, you actually get the whole data set, but you see it's actually stored inside of a list, and this list is one record long. So just like we saw one table here with one list, we actually need to get to the first record in that list, which is the only record. And so whenever we printed it out, whenever we called this implicit print operation, it says, okay, well, for record one in this list, it's this one big data set. So all I did here is I just went ahead and went to that first record, and then now you can hit $sign, you can see all those columns. So that might be convenient at some point, but anyway, we're not totally done. All right, so cool, I can nest this. What the heck is this for? This is useful because now we can actually perform our linear regression inside of our whole operations here. So for this, we're going to use another function, and this is one that you may not have seen. It comes out of per, and it's called map. And basically, this just allows us to apply a function to a list of data a list in our data. So in this case, our list, if you see here, this is a list data type that we call data in our tibble. We can apply our linear regression to our data. So the first argument here is this .x. That's actually like, what am I applying this to? And we call it data, just that's what it's called right here. And then what are we applying? This little tilde here, this is, again, potentially kind of a, it's the formula notation I was thinking, and I typed it. But we're actually going to do the linear model, just like we did above. And we can actually just straight up copy most of what we had up here. But instead of data equals, some sort of reference, we're actually going to reference the data that we have at this point. And to do that, we just use this dot. So that dot will tell us, or it tells the modeling method, hey, we're going to use the data that's available to me, based on the order of operations at this point. So if the pH has been exponentiated, then I'll get that data. But if it hasn't yet, then I'll get whatever data I have available. So if we do this, now we get the output here. The tibble. Now we have a second column here, right? Because mutate creates columns, or updates columns if it already exists. And this is a list, and you can see this type here is a linear model. And this other list, this data here, this is a tibble. So we have the linear model for this tibble, just stored straight in a data frame. So that can be kind of convenient. While we're in here, we can go ahead and calculate what our R squared is going to be. I'm just going to throw one in here for just a second. What our mean absolute error is going to be, and our root mean squared error is going to be. And we can get our predictions. So we're going to kind of do this all at once. So just like up above where we use map to get our model, which was using an input, which was data, which is a list. And in this case, we're actually going to need, just like up above here where we use predict, we use the linear model and the data. Both of these are lists, so that means we can actually continue to use map, and there's actually another function here called map2. Here's that map2 double that I was talking about a second ago. We can use map2, and the first argument, just like up above, is the linear model, so that's called bit. And the second argument above here is the data, so that's just called data. And we can call predict on this. So if you leave it just like this with no arguments or anything, in this case there's not much more to add to predict, so no need. Then we can just call predict just like this, and we should now get a list of predictions. So if we test this out, now we get a list of predictions the same length as our data, and it's a double, which is fantastic. So now we have our list of predictions, and our ones for R squared, MAE, and RMSE, which we can fill in. So let's go ahead and calculate those variables. So in this case, so map2, this returns a list because we didn't need the value to come back, since all this data is aggregated at a one row level, and I'll show you in a second how this gets really, really powerful. But for now, all this data is aggregated at one row level, but we want R squared, MAE, and RMSE to be printed out to the screen. So, or at least to this this data frame. So what we can do, just like up above, where we call caret R squared, we can attempt to call predict. It's called pred. That's our prediction. So pred equals pred, which is why I called it that. And obs, this one is actually inside of our data, and it's called quality. So if we just try to do this, actually what this has done here, it's trying to go up the chain here and try to find this data quality. And we can certainly try this, but I don't think this is going to work. We're going to have to call this with map. And actually what we can do is we can do map double. And just like up above, where the argument is the, where the arguments are what's the inputs, I think we can actually do map2 double. And we can see how this goes. So the first thing we need, the first argument is going to be, we'll just call this .x is pred, and .y equals data. And then here, now we can say, okay, pred, this is actually just .x, and this is .y, but it's the variable quality here. So let's see how that works. And so now we have our R² value. So, and because we called it as a double, we actually got to print it out to the screen straight up. But if we let this double out, we would get a list with just one variable in it. So in this case, we're able to kind of extend it out. So up to you to your preference of how you prefer to do that. But this is one option. So and then I'm just going to just go in here and change R² to MAE. Whoops, and I'm going to kind of just copy this down. And we're going to put this in here too. One interesting hotkey, I'm not even sure why it's in here, but you can hit Shift, Alt, and down, and it will duplicate the line. And so if you're like kind of making these variables, one at a time or something, you could certainly do that. So if copying and pasting isn't necessarily your thing, that's definitely an option for you. So, all right, so now I've got my outputs here. These are the same values as we had above, and I can just prove that here really quickly. So 0.361, it just does some rounding for presentation, but it doesn't actually do any internal rounding. These values are exactly the same, and actually I can prove that. So if I do this R², so this is just going to be the one value of R². So these are exactly the same. So so we have our outputs. Okay, so you're thinking, okay, well this is like a neat trick or whatever, but like why is this useful? So this could be useful if you had some sort of grouping variable in your data and you want to create multiple models for each of those groups. So for example, if you we don't actually have a grouping variable in here, but we can create one. We can call it group var, and let's just make it a random number. So we can just call it runif. And then we'll do n is equal to the, it's just equal to n, and we'll just go between 0 and 1. All right, so I think if we can just test this really quickly. So n, this is just the number of rows that comes out of your data set. So now we have a new variable called group var, and actually we can group by that group var. This is just this is a function that's inside this tidyverse. It's actually coming out of a package called dplyr. And then we can just take a quick count. Tally is that count here. And this is actually my fault. Our runif, our uniform, this is a uniform distribution, just comes out of R. This is a uniform distribution, and actually it's these are decimal numbers, so we need to round this, so no big deal. And one thing to note about this is if we were going to do something like this, this gets recalculated every time based off of a random number, a random seed. So if we wanted to be super specific and we want to make sure our numbers are reproducible, and for you, I definitely would want to, then we can take a look at this. And now if we do the same thing. Oh, another quick tip, this actually comes from console days. If you type a little bit of what you're planning on doing, you can hit Control R, and that'll pull up recent things in the terminal that you've done. So since the only thing I did is I updated that code, now I have 0 and 1. So if I was going to run this again without setting my seed again, just for posterity, and I can also hit the up arrow in the console. Look at this. So we have 810, 789. I haven't reset my seed, so I'm going to get a different number this time, 838 and 761. But if I do set my seed, again, you don't necessarily have to do it on the same line. I'm just to speed it up. It's set.seed, of course. So I didn't actually set the seed the first time either. My bad. So we're going to get a different number, but that's okay. So just to prove it here, we set the seed. We're going to check this out. Group by, okay, 816, 783, which is a different number than we had either one of these times. And if I was going to run it one more time, and we don't even have to set it to that variable, we can just do this. So group by, group var, and then tally. And so now we have another number here, but if we set the seed again, just to prove that we can get this reproducibility, now we can do, we should get this 816, 783 here, because that's when we set the seed. So group, And there it is, 816, 783. So anyway, so that's one way you could get reproducibility if you're trying to get other people to reproduce your work. So in this case, we're going to group by this group var, and all we got to do that is use this group by just like that. We've already set it, so it should be good to go. And then one thing we'll have to change here in our nest, this says everything in it, but we wouldn't want to actually group by that group var. So if we take a look at this, what we get the output here, we'll actually get 2. So before we had one line, so one tibble for all the data, but actually now we're gonna have 2. So we're gonna have 1 for each group var. So and this is half the data. So this is, and I didn't actually set my seed again, so let me do that. So give me 1 second. All right, and then now if we take a look at it, there we go, that's 816 and 783 again. So now when we create our fits or predictions and stuff, we can actually get that for each variable. So now for our grouping variable, if we did have something, we could get 2 separate models, 2 different predictions, R-squareds, and MAEs for each of these. So if there is some sort of natural grouping, this would be pretty convenient. All right, well, I think this is a nice natural stopping point of this one. I'll see if you guys have any questions about anything in particular, and we can go from there. Please feel free to ask any questions in the comments, and I'll be happy to answer them. Thanks.